So, hello everyone, I'm Gisela Camacho. I'm a second year PhD at the Institute of Space Science in Barcelona. And here I will talk about the set that is called Shear ratio. That is the collaboration that I'm in, Dark Energy Survey with David, and I will explain my work here. I'm not going to do any spoiler of the data, so you have to wait until the end of this. Okay. So first of all, I want to do like a big picture, like what we are all here. We are cosmologists. We want to answer some questions like what is dark energy, what is dark matter. So to do that, one way to do it is like we build telescopes on the Earth, we send it to the space, and the data that we can obtain can be either photometric or spectroscopic. I will focus in photometric surveys because it's what this is, and also is like a weak lensing survey. So why photometric surveys? It gives us a lot of high efficiency and depth, but the thing is that the redshift precision is quite low. So for that, we need tools to calibrate better the NFCs. Why? Because our cosmological constraints depend significantly to this. And this is where shear ratio enters, because it can help us to know if our redshift distribution, like the high sources, are well enough. So first of all, what is shear ratio? Shear ratio is simply so galaxy-galaxy lensing. You do the ratio, but you are using the same lens. But first, what is galaxy-galaxy lensing? Galaxy-galaxy lensing, it measures the effect that we have some foreground galaxies that affect the shapes of the background galaxies because of the mass that are between them. So when you look and you correlate the position of the lens with the shape of the sources, you see that it's not random. There is some correlation, there is some distortion there. That what happens is that there is this stretching here, and this stretching is tangential to the lens. So this is what we call tangential shear, and is what we use to calculate shear ratio. So one way to calculate tangential shear is a more physical way is through the excess surface mass density. This excess surface mass density is this here. So this only depends on the length. This is the important thing now. And then you divide it by the critical surface density, the symmetry, that it only depends on the distance and also the cosmology. So the cool thing about shear ratio is that, okay, we are going to divide this gamma t, this tangential shear, but we are going to use the same lens. So the thing is that we get rid of this excess surface mass density, and we intend something that only depends on the distances. This right here, and then you have here the formula, and you see that only depends on the redshift distributions. So I create this GIF. I guess it's going to make things simpler. So here I create like this ideal case of how this redshift distribution really cool because they are really thin. In reality, it's not like this. But to see better, to have this geometrical shear ratio calculation, I create this lens and then these source bins. And what happens is that, okay, for example, in the red line, you have you divide the lens, you calculate the galaxy-galaxy lensing with the lens and the source that is moving, and then you divide it by the lens and the ones that are fixed. So you can see as higher the source goes up in redshift, your value shear ratio goes up. And also, like, to know more or less that this is a good done, when it overlaps, it goes to 1 because you are doing the same galaxy-galaxy lensing. So what I saw is that, okay, this is really ideal. We don't have, when we do our redshift in our surveys, it's not like this. So for that, there is another way, is like only geometrical shear ratio, but also you can calculate this tangential shear doing this two-point correlation function between the position of the lens and the shape of the sources. So in year 3, Carles Sánchez and Judith Brad, what they did is they implement the shear ratio likelihood in the full model, in the cosmosis pipeline, to calculate the shear ratio using all the Nusant's parameters. So for that, what we expect is that shear ratio is going to be mostly affected with the multiplicative shear bias, intrinsic alignment, and also cosmological parameters. So after all of this, is why shear ratio it can be that it's a little bit simpler, but I guess it's powerful because it's simpler, so you will see. But the thing is that shear ratio is an additional and independent validation test for the source galaxy samples, and test this is always good. Also, shear ratio is really sensitive to the mean redshift. So as I told, our cosmological constraint depends significantly to this. So if it's sensitive to it, it can help us a lot. And also we can calibrate multiplicative shear bias. Apart from that, shear ratio comes from galaxy-galaxy lenses. So if we are calculating shear ratio to high redshift sources, we have more signal, but are the ones that are more complicated to calibrate. So good point. And then another thing is that for example, in the DES, we have different sources of information like cosmic shear, 2 times 2 point, 3 times 2 point. So what we do with shear ratio, we want this to have no correlation with any of this. So what we do is like we take the galaxy-galaxy lenses, but our maximum scale is going to be the minimum scale that we are going to do for galaxy-galaxy lenses. So we know that the information that we are using has no correlation. So, okay, so after all this, before starting to have the results, we wanted to know, well, in year 6, what we wanted to do is that, okay, we are going to use only the shear ratios that are the most fully geometrical. Because in year 3, they use 9 shear ratios that are these ones. But here we want to decide, okay, we are going to know the ones that we almost don't have any nuisance parameters that affect. So for that, here, what I have in the left part is the shear ratio. And what I compare is this full model and compare it with the geometrical one. As you can see, more or less, it's quite similar, so that's good. But then another test that I did is that, okay, we are going to calculate with the full model shear ratio with different intrinsic element parameters, and we subtract the shear ratio with no intrinsic elements. So as you can see, there are 2 shear ratios that they don't care about any intrinsic alignment. So, okay, we decide we're going to keep these 2 and do the test with this. So then also you can see here is that the redshift distribution for year 6, for the next year 6, and the ones that are colored is the ones that we are going to use for shear ratio. So we are going to use the lens ones. This is like the notation I will use, like 1, 2 is the lens beam, and 3, 4 are the source beam. You can see that mostly they do not overlap, so that's good, because it's when intrinsic alignment can affect the most, but there is some overlapping effect. But also, like, when we see this, we also check how other nuisance parameters can affect shear ratio. And we see that there is almost no impact in our posterior, so okay, let's continue to this. So this is the first result I will show. What I have here is like the shear ratio space without the 2 shear ratio that I calculate. And the yellow thing, well, the yellow counter is I took the galaxy-galaxy lensing for the unblinding data vector for year 6. I divide it, I calculate the shear ratio, and is what I obtain. And then I compare this to this fully geometrical calculation of shear ratio that are this one. Well, I cheat a little bit. Here we have multiplicative shear bias because, yes, shear ratio cares about multiplicative shear bias and can help to calibrate. So as you can see, here I have how I calculate the ones that are not yellow is using different samples on N of Z, because Marie explained a little bit how you have to calibrate your N of Z. So in this we have different steps. We have some BZ, WZ, and also correct for the blending. So this is what are different N of Z calibrations. So the one that we need to compare here are the ones in yellow compared to the final, that is the green one. And it's like less than 1 sigma. So this is consistent, so that's good. And then the last plot I will show is this one. There is a lot of information here. I hope I will be as clear as possible. Here we have the posteriors of the values of the multiplicative shear bias and the errors of the mean redshift. We only have these 2 because the only sources that we are using for shear ratio are the beam 3 and 4 in source. So here I'm comparing two models different to calibrating of this that we are using in this. So for example, in year 3 and in most of the surveys, what they do to have the posterior of the error in the redshift, they have the mean redshift and they have allow for some shift. So this shift can go to minus 0.1 to 0.1. But this is what we call flat priors. But then also in year 6 we have a new implementation that is called modes. Please don't ask me a lot about this. If you want to know something, there is Gary Bernstein, and good luck reading the paper. So we wanted to see if how far this new implementation of this new way to calibrate the redshifts compared to the one that we were used. And as you can see, for example, here, you can have to see how far are the purple one with the pink one, because these models are two independent models, and these are 1.77 sigma difference. So we can see that this is consistent and the shear ratio test pass. So yeah, and no, yeah, that's okay. Thank you. We have.
Thanks for nice talk. So remember for this year 3, the shear ratio was used for the cosmological analysis as well.
Yeah.
Here you showed like using it to see if your estimates of the calibration parameters is correct or not. What's the plan for this year 6?
At the end, we decide to do not use in the analysis, because when we implement the modes, I run some tests and we see that we don't gain that constraint in shear ratio. But for me, I guess this why I think modes is quite powerful.
Thank you.
Any other questions? Okay. Thanks again, Gisela.